let's go through another quick example that shows us how to populate the values in our product of exponentials formula. So here we have a product of exponentials formula that describes the 4 joints in this open chain. 3 of these joints are revolute and 1 of them is prismatic. And the axis of rotation of each of the revolute joints is in the z direction. So the first thing that we want to do when finding the values that make up our product of exponentials formula is find the M matrix. And our M matrix will represent the homogeneous transformation of the end effector in the reference frame. And for our case, we'll choose a coordinate system for the end effector that has the same coordinate directions as our reference frame. So there's no rotation between the 2 states. There is only displacement. And so again, we have a homogeneous matrix. Our displacement in the x direction is 0. Our displacement in the y direction is L1 plus L2. And our displacement in the z direction is L0. And finally, the last value in this row is a 1 because we have a homogeneous matrix. So next, let's define the values of omega. And again, omega is a value in our S matrix in the exponential form of screw motion that is a unit vector in the direction of the screw motion. We can also define it using the skew symmetric matrix format, and that will go into, that's actually what's used in the product of exponential notation. But for now, let's just use a unit vector. So let's get a table started to write down our values. So the first joint is a revolute joint, and its axis of rotation is in the z direction. So what that means for us is that omega is a unit vector pointing in the direction of z. We know the same is true for joints 2 and 3 because they're revolute joints with their axes lined up with joint number 1. For joint number 4, it's a prismatic joint, so it doesn't have any rotation. So all the values for omega are going to be 0. Next, let's find the values of v. So normally, we find v using the formula of negative cross product omega and q plus h omega, where h is the pitch of the screw motion. But in our case, h is 0 because these are revolute joints and they have no pitch. So we can just find v using the cross product of the negative cross product of omega and q. So let's go ahead and define q for each of these joints. So for the first joint, a convenient choice of q will be along the axis of rotation, and so we can choose it to be the origin. And that makes it easy to find v. We just simply know that the cross product of omega and q is going to give us a vector of zeros. So we can do the same thing for q for joints 2 and 3, but they don't have axes that go through the origin. So instead, we'll have to choose values of q that lie on the y-axis. So we can find q for joint 2 to be L1 it has length L1 in the y direction. And so if we calculate the cross product of these, the negative cross product is going to give us L1, 0, 0. And so joint number 3 is pretty much the same process. And we can choose a value of q that lies on the y-axis and is L1 plus L2 distance away from the origin. So again, if we take the cross product of these two, of omega and q for joint 3, we get an answer that is similar to joint 2. So moving on to joint number 4, this is a prismatic joint, and we already defined it to have no rotation. So in order to find our vector v, we've already mentioned how to do this, and it's just a unit vector in the direction of displacement of the joint. So since this prismatic joint moves only in the z dimension, this is our unit vector describing that. And so finally, let's go over again what these values will mean in our exponential notation that makes up the product of exponentials formula. So again, S is defined to be the matrix with parameters omega and q, or omega and v, sorry. But V takes the form of the skew symmetric matrix shown here. And so using S and the displacement or the rotation of the joints theta, we can calculate the forward kinematics of our joint arm using the product of exponentials formula.